Welcome back. In this section, section 4.2.2, we'll be looking at the fundamental theorem of calculus. All right, so in this section, we will describe an efficient way of computing the integral from a to b of f of x for a vast range of functions f of x. All right, theorem 4.2.2, fundamental theorem of calculus. Let f be a continuous function on ab, then the integral from a to b of f of x dx is, so it's going to be g of, g of b minus g of a. So where g is any antiderivative of f. So you find an antiderivative, you plug in b, you plug in a, you subtract what you get, that's what you need. All right, to simplify the notation, we will write the integral from a to b of f of x dx. We'll write it as g of x. So we'll just, in the first step, we'll just find the antiderivative and we'll leave the bounds, just put them as a line, and then we'll plug it in. That's going to make it easier to keep everything straight. All right, so let's try to do examples using that theorem. So evaluate the following integrals using the fundamental theorem. Just by the way, we'll call it FTC often. All right, so for short. All right, so what I'm told is I have to find an antiderivative. So I need to integrate this function in the chapter 3 sense of integrating. So 2x squared is 2x cubed on 3. 4 is 4x. And then I'm going to put my bounds here. That's this part. Then I'm going to plug in 5 into both terms. So that would be 2 times 5 cubed over 3 plus 4 times 5. And then I'm going to plug in 1 here and here. 2/3 plus 4. All right, so really this is my g of x. It's an antiderivative for 2x squared plus 4. And then I plug in the values. This is my g of b. And this one is my g of a. All right, and now we can simplify the answer, and I got 296 over 3. (296/3) should be familiar. This is the value that we got right here because we'd done it in example 1.1.9. All right, so look at the amount of work I had to do, barely any. And let's go back to where was it? 4.1. There you go. This is the amount of work, right? I had almost a full page, didn't have enough room, it was all stuck, tons of work, tons of possibility for error. All right, so we really like this FTC. It's going to be super helpful. Not only will it make it easier to compute integrals of polynomials that we could already do, but it's going to allow us to integrate functions that are way more complicated than polynomials. All right, so let's do this one. I can bring the 4 out. Then I need to integrate this function here. That's one of these arctan with a squared equals 9. So a squared equals 9, a is 3. And so I'm going to get 4 1/3 arctan of x, and then from 0 to 3, no, x on 3, sorry. 1 over a arctan of x on a. I'm going to plug in 3. I'll get 4 times 1/3 arctan of 3 on 3, arctan of 1, and then 1/3 arctan of 0. And now I just need to evaluate these arctan. Arctan of 1 is pi on 4, so I get 4/3 times pi on 4. Arctan of 0 is 0, and so that part just goes to 0. Right, so this simplifies to pi on 3. Right, let's do a final one. Integral of cosine. Integral of cosine is minus sine. I have a definite integral with bounds, so I need to plug in the bounds. So I'm going to get minus sine of 2 pi minus sine of pi on 4. All right, 2 pi, you could plug it into your calculator, but 2 pi is a full turn, so the y-coordinate would be 0. And then sine of pi over 4, we've seen often is root 2 on 2. And so my answer is root 2 on 2. It's good to remember at this point that all of these computations are about area. So we'll do problems with area in the worksheet, but really what we found is this taking the antiderivative and plugging it in. That's a really nice and straightforward way to compute complicated areas, right? Even this one was a bit complicated and we got the answer in 2 seconds. All right, so in the next section, in section 4.3, we'll be looking at the techniques of integration that we've learned in the past. We'll be looking at substitution and integration by parts, but we'll do them for definite integrals. So we'll do them with bounds.